All right, let's dive right into this explainer. Today, we're going to play the role of patent examiners to dissect a really fascinating intellectual property mystery surrounding U.S. patent number 12,664,142. Welcome to Part 8 of our 12-part series analyzing this architecture. Today, we are focusing on the prior art battle. We're distinguishing historical hierarchies. Because, what happens when a modern patent claims to unify data and execution, but computer history shows us we've been trying to do exactly that for over 50 years? Well, we're going to find out. So here's our docket for today. We'll start with number 1, our target, HSDB. Then we'll look at Challenger 1, mumps, Challenger 2, active XML, and Challenger 3, DOM execution. We'll lay it all out in the prior art matrix, and finally, wrap up with the mathematical divergence. You see, computer scientists have literally spent decades trying to merge data and execution. It's an ongoing saga. We're going to be jumping from a 1966 hospital mainframe to the peer-to-peer web of the 2000s, into modern web browsers around 2014, and finally arriving right in the 2020s with our target architecture. Okay, Section 1, the target, HSDB. Created by researcher and legal scholar Kyle MacLean Smith, the Hierarchical Script-Database, or HSDB, which is commercialized under the name SeedTreeDB, dynamically evolves by putting nouns, meaning the data, and verbs, the instructions, right next to each other in one cohesive structure. So instead of having a traditional database schema sitting way over here and your application logic sitting way over there, HSDB uses a completely unified JavaScript kernel. It totally eliminates that clunky translation layer between the two. And that means your database can instantly and actively evolve in real time.
Let's move to Section 2. Challenger 1, mumps.
Step back in time with me to 1966 at Massachusetts General Hospital. Running on a tiny 8-kilobyte PDP-7 machine, mumps was absolute tech archaeology magic. I mean, it pioneered NoSQL concepts decades early by using what they called globals. These were persistent, schema-free, sparse arrays, meaning the system only took up disk space for the data that actually existed, rather than forcing everything into rigid, empty tables. They were stored directly on a disk and accessed simply by slapping a caret symbol right before a variable name. No create table command needed. You just assigned a value to a hierarchical path, and the system dynamically built the tree. And the really brilliant part is how a hierarchical model using array references perfectly matches the tree-structured nature of a patient's medical record. Think about it. A patient has labs. Those labs have results, and those results have values. Mumps stored this data incredibly naturally as a tree, allowing multiple doctors and nurses to access and update it concurrently. It was a completely revolutionary approach to active hierarchical environments. So, the crucial takeaway here is that while our modern HSDB uses a unified JavaScript kernel, mumps pulled off its magic by storing character strings on disk and running them dynamically using the native execute command. In mumps, there is basically one universal data type, the string. So a piece of data and a piece of executable code looked exactly the same to the database. You could pull a string from a node and immediately evaluate it as programming code. It was a super clever, albeit physically disk-bound way to encapsulate logic inside a database tree. Let's jump forward a bit. Section 3, Challenger 2, Active XML. Born out of INRI's research in the early 2000s, active XML documents contained both static data nodes and active function nodes. This allowed the database to dynamically grow through a process called materialization. Instead of just storing static, boring tags, an active XML document could actually house a function. When that function was triggered, it would reach out across the network, grab fresh data, and weave it directly back into its own structure. It's basically a declarative, peer-to-peer framework physically expanding itself. The step-by-step logic is so cool. First, an event, like a user query, triggers an embedded AXML call tag. Second, that node invokes a remote web service, usually using SOAP or XML RPC. And third, the results are materialized. They are merged right back into the XML tree where the call was originally made, physically growing the database in real time. Now, pitting them against each other, HSDB keeps all its execution inside a homogeneous, continuous JavaScript kernel. Active XML, on the other hand, relies on external service calls to gather new data. So while active XML is incredibly powerful for distributed networks, its execution plane is fundamentally external to the document itself, and that creates a physical boundary that HSDB specifically aims to eliminate. All right, Section 4. Challenger 3, DOM execution. Moving to 2014, this challenger is grounded in something you literally use every single day, your web browser. Under the Document Object Model, or DOM, HTML trees encapsulate JavaScript which speculatively runs in a sandbox, actively altering the document's hierarchical state. Actually, this is the exact reason why modern web pages seem to load so incredibly fast for you today. To discover and prefetch hidden resources, like images or extra scripts, a browser will execute encapsulated scripts within a secure engine before it even renders the page. The execution of these scripts dynamically grows and alters the document tree. It's a very modern, heavily utilized example of event-driven dynamic growth happening within a hierarchical structure. Okay, section 5. Let's look at the prior art matrix. When we synthesize this intellectual property battle and map these systems side by side, a really fascinating pattern emerges. We've got mumps using strings via execute, ActiveXML utilizing call tags for materialization, and the DOM using script elements for prefetching. It clearly shows that embedding executable logic within tree nodes for dynamic growth is a well-established paradigm across all these eras. The prior art proves that the actual idea of an active hierarchy is not new at all. But look at that final row for HSDB. The growth method is listed as mathematical coordinate expansion. That right there is where this entire story takes a sharp turn. Which brings us to section 6, mathematical divergence. If they all do dynamic growth, what is the ultimate resolution that makes HSDB uniquely patentable? Well, HSDB utilizes this specific infinite stack index formula, which is termed Pythagorean metal. Unlike mumps or ActiveXML, which rely on physical memory addresses, tags, or disk arrays, HSDB treats code and data as isomorphic entities. That means code and data become literally indistinguishable from one another. Instead of relying on physical addresses, kind of like a map, it uses pure geometry. It uses the continuous infinite diagonal of a right triangle to mathematically generate the unique coordinates for its data. It uses this formula right here, c minus b over a, all to the power of n. And it uses that to generate infinite, self-reproducing input-output data. So what does this actually mean for us? It means that, unlike those older systems that rely on disk journals or append-only constraints, if HSDB loses a state, it can mathematically derive it back using geometric series logic. By modeling state transitions as iterations along an infinite geometric number line, the database's execution path and its data retrieval path become the exact same thing. It is a purely mathematical guarantee of consistency, completely removing the traditional reliance on physical hardware limits. It's a fascinating convergence of computation and intellectual property to think about. We've seen how historical systems like mumps and ActiveXML totally paved the way by embedding logic into data structures. But HSDB takes that final leap by mathematically fusing them into a single, non-halting entity. As autonomous workflows rise, will data and logic ever be truly separated again, or is this total convergence the only path forward? I really hope this explainer leaves you eager to explore the future of database architecture. Thanks for joining me for part 8 as we unravel this prior art battle and keep questioning how the data structures around you are built.